And we're back. Okay, so this is the beginning of section 2.5. Hi, Miss Snapples. What? Yeah, that's okay though.
The last question, 13B, how many points did you like the written out answer be? 1 or 2?
The written out answer? I haven't gotten there yet. I'm doing page by page. How much are you doing?
I don't know. I'm thinking 1.
Yeah.
Because the work up above.
It's the good stuff there.
1?
Yeah, I agree. Okay, so section 2.5, this is all about continuity. There's several more sections within chapter 2. Then we will take our chapter 2 test. Just so you guys know, I do not know. I haven't really planned out that far when our next assessment is. Oh yeah, I have. We are not going to have our another assessment before the end of the 9 weeks. So those of you not taking this for CCP credit, those of you taking just for the honors credit, hey, come on in. Oh, I thought those were like donuts or something. That's next. So those of you for taking it just for the honors course and not the CCP credit, that matters a little bit more to you guys than it does to those of you taking the CCP credit. The CCP credit just like rolls all into one. It doesn't like break. It doesn't like start fresh or anything. So you just get your whole final semester grade. But again, we will not have any other quizzes or tests beyond or before the first 9 weeks. I did, and I should do that. Maybe I'll do that sometime today. I did run the CCP averages. Oh, that's right. I was waiting until I graded the limits quiz. I did run the CCP averages. I have to make up a spreadsheet with all of the correct calculations. So I will do that, and then I will post it on Canvas. As soon as I get the limits quiz graded, I'll put everything into that Excel sheet. I have it arranged by student ID, so it's not, you can't tell whose is whose. But I'll put it all into a spreadsheet and then I'll upload it to Canvas and I'll send out a message when hopefully sometime this weekend I'll be able to do that. If not, then by Monday. All right, enough of me talking. Let's get to it. Section 2.5 is continuity. We noticed in section 2.3 that the limit of a function as x approaches a can often be found simply by calculating the value at a. That's direct substitution, folks. Simply just plugging in the value at that point where it's going to. Functions with this property are called continuous at that point. Continuous. Continuity is very, very, very important to know because if you can tell something is continuous, you can use direct substitution. Okay? If it has that property where you can use direct substitution, it is continuous, and if it is continuous, then you can use direct substitution. Now, how do we say what is continuity? What is continuous? Well, we'll see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language. There's a lot of different ways we can talk about continuity. There's, continuity of government, where we know exactly, if the president dies, who is next? If that person dies, who is next? And so on and so forth. We have that continuity of government where there's no gaps or breaks in the line of succession. There's this thing called continuity in like movies and film, where if the actor's in one outfit in a scene, and then it cuts, they have to do like another cut of that same scene, but oops, they didn't have that same outfit on that same day, and then they're wearing like a blue shirt instead of an orange shirt. That's going to catch your eye, and that's going to be like, wait a second, his shirt just changed colors in the middle of the scene. You're going to know that. So there's a gap, there's a break, and your mind goes to something different, right? So that word continuity kind of means this exact same thing. There's no gaps or breaks within the function. There's no gaps or breaks within the function. Okay? A continuous process is one that takes place gradually without interruption or abrupt change. So here is our mathematical definition of continuity. The limit as x approaches f of x is equal to f of a. Okay, so direct substitution. Yeah? But the thing is, we're saying everywhere around a, on an open interval where a exists. So we're saying that as long as a is in this open interval where a exists, you could take the limit as x approaches a of f of x, and it will equal f of a. If this is not true, then the function is not continuous. So if you can show that there's a place where the limit does not exist, or where the left side limit does not match the right side limit, or some place in there where it's not a f of x is equal to f of a, then it is discontinuous. Then there is some sort of discontinuity. Notice that definition 1 implicitly requires 3 things, and this is something to write down, these 3 things, because this is the way to show continuity. First of all, f of a is defined. F of a has to be defined. F of a has to be equal to a number. Okay. F of a must be defined. Meaning, you can't have that, those rational functions where one cancels out. Yeah, that means it's discontinuous. That means there's a discontinuity. The second thing here is the limit as x approaches a exists. The limit must exist, which means there can't be any infinite limits in there as well. And the limit as x approaches a of f of x has to equal f of a. I mean, this is the basic definition, but that definition requires the first 2. F of a has to be defined, and the limit must exist for all places around a. The definition says that f is continuous at a if f of x approaches f of a. The definition says that f is continuous at a if f of x approaches f of a as x approaches a. Thus, a continuous function f has the property that a small change in x produces only a small change in f of x. In fact, the change of f of x can be kept as small as we please by keeping the change in x sufficiently small. So let's talk about what happens if there is some sort of discontinuity. All right, if f is defined near a, we say that f is discontinuous if f is not continuous at any point in a. So what can happen? Let me actually jump down to this slide, because the book doesn't actually define how we talk about discontinuities. This is the way that I learned it when I was in calculus, and the AP Calc book actually uses this language as well. So I'm going to jump to something like this. I would jot these down. I would know what these look like and how to describe them. Because when there are discontinuities, I will talk about them and I will say, okay, what type of discontinuity is this? What do you see? What type of discontinuity is there here? So for example, our first type of discontinuity is when we remove a point out of the function. So there's an open circle, there's a hole in the graph, and it's removed out into a different place. The point has been removed. That point can be removed and put somewhere else. That point can be removed and not put somewhere else as well. That, again, is called a removable discontinuity. A removable discontinuity. Second type is called a jump discontinuity. This is when we have piecewise functions, and then one is, they're kind of separated at the boundary line. That is called a a jump discontinuity. It jumps from one place to the next. And then we have an infinite discontinuity, where there is some sort of limit as x approaches a going to infinity or negative infinity. So we have these 3 types of discontinuities: removable, jump, and infinite. We're going to have to look at them and then talk about them in these terms. And I'll say, okay, are there any discontinuities? And then if there are discontinuities, what types are they? Okay. Had to kind of supplement the book a little there because they don't use this terminology. All right, can we take a look at some graphs? Just like we had where we had to define where the limits were and all this funky piecewise function. You'll have some on your homework where you'll be given a graph and say, what types of discontinuities do you see, or where do the discontinuities occur? when the book asks where do the discontinuities occur, say where they occur, like these are all occurring at A, right? Say where they occur, but also I'd like you to supplement that and say what type of discontinuity it is, okay? Because I'll be asking you to do that as well, but the book may not ask it. Figure 2 shows the graph of a function f. At which numbers is f discontinuous? This is the prime example. I'm going to say where they're discontinuous and then also state why. State what type. All right. Where is f? Where are the discontinuities? 3 and 5 and 1. Right. There's a discontinuity at 1. There's a discontinuity at 3, and there's a discontinuity at 5. Okay, what type of discontinuity do I have at 1? Removable. What type of discontinuity is there at 3? Jump. And then at 5, another removable. Right. Good. So that's the exact same type of thing I'll ask you to do on your homework. It won't really tell you, okay, state which type, but you should state which type. All right, let's take a look here. Where are each of the following functions discontinuous? Where are each of these functions discontinuous? All right, taking a look at my first one there. Where is that discontinuous? At 2, right? Do I even need to factor it down? I mean, if we were actually going to graph it, if we were really going to graph it, I would factor that down and then I would say, okay, x minus 2, x plus 1, the x minus 2's cancel out. And then I would have just f of x is equal to x plus 1, right? You might be tempted to say, well, then there's no discontinuities. But there's a hole in there, right? There is a hole in there at 2. So we would say it's at 2. And when we want to say what type, if there's a hole in the graph, what type of discontinuity is that? Removable. Your calculator will not show a removable discontinuity. Okay? Your calculator will not show a removable. Like if I graph this, it's going to look like x plus 1. It's just going to look like a linear function with a slope of 1 and a y-intercept of 1. It won't show the hole. If you go to the table and look at 2, it'll say undefined, but it won't physically show a hole. So don't just throw it in your calculator and try to look. Okay, take a look at part B there. All right, where do you think the discontinuity is going to occur? Where do you think the discontinuity is going to occur? Where at? At 0. At 0. Because what happens at 0? It's at 1, right? It's at 1. Now, this one is kind of interesting because you think about it as a removable, right? Because it's taken out and put somewhere different. But what type of function is 1 over x squared? Let me get these out of here. 1 over x squared. Zoom 6. You want to change your answer now? Is it really a removable discontinuity? No, this is actually an infinite discontinuity. It's an infinite discontinuity at 0. A removable discontinuity is one where the limit exists on either side, and that point has been taken out. Okay, now take a look at this one. You know, this is the same function as in A, but now I'm defining 2, and I'm saying 2 is at 1. There's a point there, 2, 1. Now, looking at that function, I said that we could factor this down to make it look like x minus 2x plus 1 over x minus 2, cancel, x plus 1, right? Where did the hole occur? It occurred at 2, right? It occurred at 2. So now I'm saying that there's a hole at 2, and where is it filled in? Right? At 2. However, be careful here. If I have this line and it's y equals x plus 1, so here's 1, okay? The hole is here, right? At 2 comma what? 3. 2 comma, we can erase it. 2 comma 3. 1, 2, 3, somewhere like right there. There's my hole, right? And then I put that point at x equaling 2 at 1, right? So is there still a discontinuity? Yeah. Discontinuity at 1. And what type? Removable. It's only a jump if the limit does not exist. Does that make sense? I probably should have stated that a little bit clearer. Look at a jump. The limit does not exist on a jump discontinuity. The limit exists on a removable discontinuity. It's just f of x is not equal f of a. Okay. So now that's still removable. Okay. Now let me ask you this. What if I had said this? Oh, sorry. Pretend I didn't say 1. Pretend I said 2. Because it's always the x value where it occurs, right? So what if I had said this? What if I wanted to change this problem and I had said, instead of putting that point at 1, what if I had said this? Is there any more discontinuity? No, because I took that point and I didn't remove it and put it somewhere else. I took that point and filled in that dot. Okay? That's kind of a tricky one there. And I feel like thinking back, I feel like there's a problem or two in there where it looks like you want to put a removable discontinuity, but they defined that point to fill in that dot. Okay? They defined that point to fill in that hole. So just watch out for that. That can be a little tricky. All right, let's talk about our last one there. Example, or part D there, f of x equal to, what is that function? That's the greatest integer function. I think the best way to look at the greatest integer function is just to look at it on a graph. Where are the discontinuities? And it's D down here. Where are the discontinuities? Every integer, right? Every integer. The discontinuities are at every integer. And what type of discontinuities are there at every integer? Jump discontinuities at every integer. Yeah. So if it says where are the discontinuities, we say every integer, and they are jump discontinuities. I don't know why I put a period, but they are jump discontinuities. That's a unique one there. I teach discontinuities. We teach continuity to Algebra 1 students. Obviously nowhere near using any sort of limit notation, but we say if you can run your pencil along the function and you never have to pick it up, then it is continuous. Okay, that's an easy test by looking at the graph. So looking at these here, Oh, discontinuity. Here. Oh, discontinuity. Actually, yeah. Should have put the point there. Oh, discontinuity. There. Every time you have to pick up your pencil, there's a discontinuity there. If you can trace it along the whole way, there are no discontinuities. All right, so a function f is continuous from the right and continuous from the left. Basically, this definition is saying that you can do the same exact thing with right side and left side continuity. Just like we have right side, left side limits. Right side, left side continuity. Like for example, this next problem has no work to show with it. It's just an explanation that you could use the greatest integer function, the one that we just looked at. We could use the greatest integer function and talk about them as left side and right side continuous. Okay? At each integer in the greatest integer function, the function is continuous from the right, but discontinuous from the left. Now, why is it discontinuous from the left, but continuous from the right? Well, look at the function. Look at the graph of the function. If I look down here, we see that we were just told that it was continuous from the right, but discontinuous from the left. Okay, going from the right of each step, what do you notice about going to each integer from the right? That's the filled in dot. So therefore, I know if it's a filled in dot, then we could call it continuous. If it's an open circle, then that's where it's discontinuous. Okay, if it can reach that point and f of x equals f of a on that side, then it is continuous. It's continuous here, continuous here, continuous here. But it's discontinuous here and here and here because those are open circles. Does that make sense? So if that value is defined on that side, then you can call it continuous. If it's not defined on that side, that's when you could call it discontinuous. All right, let's do one more example. Show that the function f of x is equal to 1 minus square root of 1 minus x squared is continuous on the interval -1 to 1. Okay, so what we're going to say, we're going to look at the limit as x approaches a of this function, 1 minus the square root of 1 minus x squared. Now, what are we going to be using our a? Well, we want to use our a to show that this, look here, our limit laws say this, of 1 minus the limit as x approaches a of 1 minus x squared. Now you may be thinking, well, that's silly. Why are we doing this? Well, take a look. What's the limit as x approaches a constant? The constant. Okay, well, is there anything else that we can do? Well, yeah, we can take that limit now inside the radical. That was one of our limit laws. Of 1 minus the limit as x approaches a of x squared. Everybody follow me there? I'm just using my limit laws to evaluate this. That was one of them, putting it inside the radical. And forgive me, I just did two steps at once. I put it inside the radical and separated it. So this is now going to be 1 minus the square root of, 1 minus, what is the limit as x approaches a of x squared? Isn't it just a squared? Can't I do direct substitution there? So what did I just show? Limit as x approaches a of 1 minus square root of 1 minus x squared, which brought this down, is equal to that. What did I just demonstrate there? I just demonstrated that the limit as x approaches a of this function is actually equivalent to f of a, right? Didn't I just show that? What did I take here? I took the limit as x approaches a of the function. And I showed that if I take the limit, use my limit laws, I showed that it was equal to plugging that a in. And if you can do that, the limit, oops, yikes, get that out of there. Whatever. If you can show that the limit as x approaches a of f of x is equal to f of a, that was our definition of continuity. Okay. So we didn't use any sort of direct substitution property for the entire function. All we did was we used direct substitution on that one little piece where we said the limit as x approaches a of x squared was a squared. So when you're asked to show that something is continuous, you want to show that you are able to take the limit as x approaches a and just plug in a. Now, you have to use your limit laws to do that. You can't just plug in a because you don't necessarily know that it is continuous. You have to use your limit laws to show that it is continuous, meaning separate it all out using your basic limit laws. Show that if you plug in a, your original will actually equal to what you can plug it in to be. Basically, you're showing that. That's what you're showing. Okay. All right, we've got about 4 minutes. I'm going to stop there, and then we will do the rest on Monday.